In this video, we will discuss nodal analysis. Nodal analysis and mesh analysis are one of the most important techniques in circuit theory. In this method, we will identify the nodes in a circuit, and then we will assign some unknown voltages to those nodes. At each node, we will apply KCL, the Kirchhoff's current law, and the equations obtained from KCL will then allow us to calculate the node voltages. To explain this method, I'm going to consider this circuit. We will first consider current sources only. Voltage sources will be presented in the next video. The first task is to identify the nodes. A node is any point in the circuit where more than two components are connected together. The reason for more than two is so that we can apply KCL. Now let's consider the circuit and see which points can we identify as the nodes. First of all, we need to identify a reference node where we will assume that that is our reference and the voltage at that node is equal to 0. So in this circuit, I have assumed that this is my reference node. And therefore, I have connected the ground symbol to this point just to remind us that this is our reference node. The voltage at this node is 0 volts. As you know that voltage is always measured between 2 points. Again, we can compare this to the gravitational problem. The potential energy of an object which is a certain height above the ground is measured with respect to the potential energy of the object at ground. So the ground is our reference, and we say that the potential energy on the surface of the ground is 0, whereas the potential energy at some height will be calculated based on the height of the object. Similarly, in electric circuits, we have a reference, and at the reference, we will say that the voltage is equal to 0, and everywhere else in the circuit, the voltage will be with respect to this point. So for example, if I say that the voltage at this point is V1, then this means, and let's say V1 is equal to 10 volts, so this means that this point is 10 volts higher than the reference, all right? And because my reference is 0, therefore this will be 10 volts. All right, so after identifying the reference node, then we need to identify the rest of the nodes in the circuit and find out how many nodes we have in our circuit. So in this circuit, I will identify that we have one node over here. And you can see there are 3 components connected there, one resistor, another resistor, and a power supply, a current source. Similarly, the next node is this one. These are our 2 nodes. We will assign voltages to each node. So the first node, I have assigned it a voltage of V1. And the second node, I'm going to assign it a voltage of V2. And these are the unknown voltages that we want to find. Once we know these voltages, then we will be able to find the currents that are flowing in all the resistors. You can see that this is not a node because we do not have more than 2 components connected here. Similarly, this is not a node. And similarly, this is not a node. All right, so after identifying the nodes, now we will apply KCL to each node. Before we apply KCL, I want to remind you that Ohm's law says that V equals to IR. So if we have a resistor and the voltage drop across the resistor is this quantity V and the resistance value is R, then the current that flows in this resistor will be I. So that's what Ohm's law is. Now I want to write Ohm's law in this form, that I equals to V divided by R, because we are interested in applying KCL, which will give me currents, and then I will need to convert the currents to voltages. So according to this equation, the current is voltage divided by resistance. And you see the voltage across this resistance is the voltage at this point minus the voltage at this point. So let's say I have 2 volts over here and I have 4 volts over here. So the voltage drop across the resistor is 4 minus 2. Okay? And we need to remember that the current will always flow from a higher voltage to a lower voltage in a resistor. All right, so with this reminder, now we can apply KCL at node 1. So I want to apply KCL at node 1. The statement of KCL is that the amount of current that is coming into the node is equal to the amount of current that is going out of the node. So looking at the circuit, now I want to just assign a few different current values. First of all, we have, let's say, this current. I'm going to give it a name, I1. This current is I2, and this current is I3. I have chosen some directions for these currents. I have chosen I1 to be entering the node and I2 and I3 leaving the node. These assignments of the direction is completely arbitrary. You can choose any direction you want. It will not make any difference. Your final result will be the same as long as you keep track of the current, that the current has to flow from higher voltage to lower voltage. You can choose any directions of current. In fact, you can choose that all the currents are actually entering a node, or you can choose that all the currents are leaving a node. I have chosen this assignment in which I1 is entering the node and I2 and I3 are leaving the node. I can encourage you to change these directions, recalculate the values of the currents and node voltages. All right, so these are my directions for the currents at node 1. Similarly, I will choose some directions for node V2. The current in this resistor, which is 2 ohms, is flowing to the right. So just to be consistent, I will choose that this is I3. The amount of current I3 flowing in the resistor 2 ohms will remain the same. So therefore, the current I3 will be entering V2. Similarly, the current I2, which is flowing in this branch, and then the resistor 1 ohm, will be coming down here to come to node V2. And I will call it I2 again. Let's say the current that is flowing in the 3 ohm resistor is I4, and the current that is flowing in this branch is I5. So we have assigned different current values to each branch, and now we can apply KCL to both of the nodes. For node 1, I have current coming in should be equal to the current going out, so therefore I have I1 equals to I3 plus I2. I1 equals to I3 plus I2. So this should give me I1 equals to I3 plus I2. So this is the equation from KCL. Now I want to write this equation in terms of node voltages. Remember, the voltage at node 1 is V1, and the voltage at node 2 is V2. We see that I1 is actually 5 ampere because this constant current source is requiring that the current that flows out of this source is 5 ampere. And also the current that actually goes back into the source is also 5 ampere. So therefore the current in the branch on the left must be 5 ampere, which will tell us that I1 is 5 ampere. So we know that I1 is 5 ampere. I3 is V1 minus V2 divided by the resistance. Because I have chosen this direction that the I3 is flowing to the right, which means the left side must be at a higher voltage and the right side must be at a lower voltage. And that's why I3 is flowing from left to right, which means V1 must be a higher voltage and V2 must be a lower voltage. Therefore, I can write I3 as follows, that I3 should be equal to V1 minus V2 divided by the resistor, which is 2 ohms. So you see V1 minus V2 divided by this 2 ohms. So that will be I3. All right, so after I3, the next one is I2. And looking at the circuit, I can easily say that I2 is 3 amperes because we have a constant current source, which is 3 amperes. So that current source will force the current in that branch to remain 3 amperes, and therefore I2 must be 3 amperes. So I2 is 3 amperes. Now let's simplify this equation by multiplying 2 on both sides. I will get 10 equals to V1 minus V2 plus 6, or V1 minus V2 equals to 4. So this is our first equation. As you can see, we got our first equation from applying KCL at node 1. And also you should see that we have two nodes, V1 and V2. The voltages at these nodes are unknown. Therefore, we need two equations to solve this circuit. Although we have one more node over here, which is the ground node, but we already know the voltage at that node. So therefore, the unknowns are 2 instead of 3. Now let's apply KCL at node number 2. So now we will apply KCL at node 2. Let's look at the circuit again. At node 2, the currents coming into the node are I3 and I2, and the currents leaving the node are I4 and I5. So therefore, the KCL will say I2 plus I3 must be equal to I4 plus I5. This is our KCL statement. Now, let's see what is I2. I2 is 3 ampere, and I3 is V1 minus V2 divided by 2. So I2 was 3 ampere, and I3 is V1 minus V2 divided by 2 ohms. So this is I3. I4 is V2 minus 0 divided by 3. So we have V2 minus 0 divided by 3. I don't need to write minus 0 because that's not going to make any difference. Similarly, I5 is V2 minus 0 volts divided by 4. So that will be V2 divided by 4. All right, so this is our second equation. We just need to simplify it. First, I think I will multiply by 4 on both sides, and then I will multiply by 3, which is 12. So let's multiply by 12 on both sides. I want to get rid of the denominators. So to get rid of the denominators, I have to multiply by 3 and 4. So let's multiply by 12. So 12 times 3 is 36, plus 12 divided by 2 is 6. So 6V1 minus 6V2. 12 divided by 3 is 4. So 4V2 plus 3V2. Now, let's see how many V2 terms we have. We have 4 and 3, 7, and negative 6. So if I bring the two terms to the left-hand side, this will be negative 13. So I will have 6V1 minus 13V2 equals negative 36. So this will be my second equation. Now we have two equations and two unknowns. We have previously solved simultaneous equations when we were studying mesh analysis. Therefore, I will just present the results here. After solving these two equations, we find that V1 is equal to 12.5714. That's V1. And V2 is equal to 8.5714. These are the two voltages at the two nodes. Now let's check if this is correct. I will redraw the circuit here. So we have calculated V1 and V2 to be 12.57 and 8.57 respectively. And looking at these numbers, I can see that the voltage drop across the resistor 2 ohms is 12.57 minus 8.57. So this is 4 volts. So 4 volts are dropped across this resistor. Now, according to Ohm's law, if there are 4 volts and 2 ohms resistor, this will mean that the current in this resistor shall be 4 divided by 2, which is 2 ampere. So 2 ampere must be flowing in this branch. And now you see this should make sense because 5 ampere is entering node 1, 3 ampere goes through the upper branch, and 2 ampere must go through the lower branch because the 5 ampere will be divided in these two parts, 3 ampere and 2 ampere. Further, we can calculate the current that will flow through the 3 ohm resistor and the 5 ohm resistor. Through the 3 ohm resistors, we will have V2 divided by 3 ohms, and that gives me a current of 2.857 ampere. And the current through the 4 ohm resistor will be V2 divided by 4 ohms, and that is 2.143. So this current is 2.143 amperes. And now you should check if the current entering this node is equal to the current leaving that node. And we see that the current entering is 2 ampere plus 3 ampere. So 5 amperes is current coming to the node. And you can see if you add these two currents, this will also give you 5 ampere. So KCL is satisfied at both nodes. Now in this method, we have considered only current sources because when we are working with KCL, it is easier to work with the current sources. Now let's consider a situation in which we have a voltage source involved. Let us consider this circuit with a voltage source, and we want to solve this circuit using nodal analysis. In this circuit, I have identified 4 nodes. The reference node is at 0 volts. Node number 1, as you can see here, we have 3 different paths for the current to flow. At node number 2, we have again 3 different paths, and at node number 3, we have another 3 paths. I have identified some names and directions for the currents. So I1 is flowing into node V2, I2 is here, and I3 is in the 4 ohm resistor. I4 is coming to node 3, and I5 is leaving node 3, sorry. So we have this circuit with the value of resistances that are 2 ohms, 2 ohms, 4 ohms, and 2 ohms. These are our resistors. So I can see that I have 3 nodes, therefore I will need 3 equations. To get 3 equations, we will apply KCL at the 3 nodes. But in this case, V1 is already known. Because of the constant voltage source over here in this branch, we have fixed V1. So therefore, V1 is already known to us. So therefore, we do not need to apply KCL on node 1. And because of that, I did not identify any currents for this node. So here, because of the power supply, we can see that V1 is equal to 5 volts because it is 5 volts higher than the reference node. So this is our first equation, which means we are left with 2 unknowns only, V2 and V3, and we need to apply KCLs to those 2 nodes to get the value of the 2 voltages. So let's apply KCL at node 2. At node 2, I will have current coming in should be equal to the current going out. Therefore, I1 should be equal to I2 plus I3. I2 and I3 are leaving. I1 is equal to V1 minus V2 divided by 2 ohm resistor. I2 is equal to V2 minus 0 divided by 2 ohm resistor. And I3 is equal to V2 minus V3 divided by 4 ohm resistor. Now we have the equation in terms of the node voltages. To get rid of the denominators, I will multiply by 4. So I will have 2V1 minus 2V2 equals to 2V2 plus V2 minus V3. Now V1 is already known to us, which is 5 volts. So therefore this should be 10, and -2 and -2 and -1 would be -5 V2 plus V3 equal to 0, or I can say that 5 V2 minus V3 equal to 10. So this is my first equation. Now let's apply KCL to node 3, and over there we have I3 plus I4 equals to I5. So at node 2 we have I3 plus I4 equals to I5. I3 is equal to V2 minus V3. You see higher voltage minus lower voltage because the current is flowing towards the right. So I have to do V2 minus V3 divided by 4. So we have V2 minus V3 divided by 4. I4, on the other hand, is a constant current, which is 1 ampere. So therefore, I4 is 1 ampere. So we have 1 over here, and I5 is equal to V3 minus 0 divided by 2. V3 minus 0 divided by 2. I will multiply by 4 on both sides, so I will get V2 minus V3 plus 4 equals to 2V3, which will give me V2 minus 3V3 equals to minus 4. This would be my second equation. Again, we have two equations and two unknowns. We can now solve these equations by one of the many different methods. You can solve it by substitution, by using matrices. So after we solve these equations, we find that V2 is equal to 2.428 and V3 is equal to 2.1429. These are our final results. Now let's take a quick look if this makes sense to us. We have the node voltages identified on the circuit. Now we can calculate the amount of currents that are going to flow in each resistor. Based on the voltages that I can see in the circuit, I can calculate this current to be 5 volt minus 2.42 volt divided by 2 ohms, right? So let's say this is some current IA, and I can now say that IA should be equal to 5 minus 2.42 divided by 2 ohms. And if we solve this, this current is 1.286. 1.286 amperes are flowing in this branch. Similarly, we can find the current over here, and I calculated this current to be 1.214 ampere, and the current in this branch is 1.077, and we know that the current on the top branch is 1 ampere. So now we can see that the KCL is satisfied at each node. Looking at node 2, we have 1.28 amperes coming into that node, and the current leaving in this branch is 1.214, and also the current in the 4 ohm resistor is only 0.0714. And you can see that 1.214 plus 0.0714 is equal to 1.286. So KCL is satisfied here. Similarly, you can verify that KCL is satisfied on node 3. All right, so this was nodal analysis. I hope you enjoyed this video. If so, please consider subscribing my channel. That's it for now. I'll see you next time. Bye for now.